Okay. Hello everyone. I hope you are hear me fine. This is Peter Kang, today's host of today's department seminar. I'm very excited to introduce Professor Marc Hesse from University of Texas at Austin. So Marc did his bachelor's degree at University of Edinburgh in UK. After that, directly he went to MIT for his master degree, and then after that, University of Cambridge for MPhil degree, and then did his PhD from Stanford University. After 2 years of postdoc at Brown, he's been professor at UT Austin since 2009. And I personally interacted with Marc starting, I don't know, very early years of my PhD studies. And I've been always really enjoying the discussion with Marc from conferences, and I always learn something very interesting through his talks. So I'm really excited to have Marc presenting for us today. So with that, Marc, the floor is yours.
Well, thank you very much, Peter. I think University of Minnesota is very lucky to have you. So thanks very much for the invitation. When I chose the topic, I didn't really realize, it occurred to me later that you guys don't really work so much on planetary. But so hopefully it's something new to most people, although Peter was probably hoping for something else. So I'm going to talk about some work that we've been doing over the last few years, trying to think about the habitability of Europa's internal ocean, in particular how that relates to mass transport through its ice shell. And if none of this makes sense to you, I'll sort of introduce the whole topic. Let me see, okay. There we go. But just before we get into the details, so, I think of myself as a geological fluid dynamicist, and in my brain, there's sort of kind of three boxes. There's some of the work we do is sort of really basic, I guess, fluid mechanics, typically involves benchtop lab experiments and then some very detailed modeling. So for example, we've done a lot of work on convection in porous media driven by solutes motivated by geologic CO2 storage. And that's sort of one aspect of my work. And I tend to think of that some stuff I do is actually useful. And that typically involves field data and sort of modeling things on the field scale. So one project we've been working on, or we're working on currently, is trying to use surface deformation data, space geodesy, INSAR, GPS, to try and infer properties of shallow confined aquifers. And the hope is eventually to apply this to aquifer storage and recovery. But it's very engineering. There's no science conclusion yet. I'm getting a message. A participant has able closed captioning. Okay, sure. And then there's the fun box, and that mostly involves planetary problems. Planetary is just very good at generating sort of simple first order problems. And everything we do in planetary, almost everything we do in planetary is actually, I teach a class on numerical modeling, and every year we pick a new problem. And so, for example, 2 years ago, we built this little model of a global Martian aquifer. And so, none of this means that useful work can't be fun or fundamental work can't be useful. But anyway, this is how I've been it. And so clearly today we're going to be on the fun side. And although a lot of this work was actually done in class, so to speak, it always takes extra work to finish things up. So we've had various sources of funding from NSF, from NASA, from JPL, and now we have this Center for Planetary Systems Habitability, and they funded us too. So what I'm presenting today is the work of 3 graduate students that have then taken on these projects and developed them further, Jacob, Evan, and Natalie. And over the years, there's been a number of collaborators, all of them, well, almost all of them at JPL. So it started with Julie Castillo-Roger. Nowadays, I work a lot with Steve Vance. Purva Oza is my astronomy, the person that helps me with all the astronomical stuff. Rona Cox is at Williams, and she's helped us with the third project I'm going to introduce. And Carol Raymond, she was the lead on the Dawn mission, and she's gracefully included some of our work in one of her big overview papers. So I guess I can claim her as a collaborator. Okay, so but today I want to talk about what we generally refer to as icy ocean worlds. And they're interesting because, classically we think of the region of our solar system that's habitable as essentially the distance from the star at which surface water is stable or was stable in the past, right? And so this is the Goldilocks zone, not too cold, not too hot, just right. And currently there's a very limited number of planets that exist in this Goldilocks zone in our solar system, and by definition, unless the planets are spaced much closer together, also in other solar systems. So currently there's the Earth, maybe there was Mars in the past, maybe there was Venus in the past, but it really right now and for a long time it's just been Earth. And so that's very limiting, especially now as we think also with exoplanets, as we're beginning to explore other solar systems. And so I guess one of the more, as far as I'm concerned, remarkable discoveries really is that when the Galileo spacecraft flew through the Jupiter system and they passed by the moon Europa, they were measuring, the magnetometer was measuring the various components of the magnetic field shown here on the left. And the prediction coming from just the overall field of Jupiter would be that there's these gentle straight lines, but the measurements showed this bump. Can you guys see my cursor? Or am I?
Yes.
Okay, good. Right, so you see this bump here. And so that was an unexpected deviation. And the only way that they could explain this was with an induced magnetic field. But the thought is that Europa's core, if it has a core, is solid, so there can't be the kind of dynamo that we have in the Earth outer liquid core. So something else must be convecting to generate these. And they concluded back in the day, there must be a current-carrying outer shell of salty liquid underneath the ice shell. So on the surface, it's frozen ice because it's very cold out there. But underneath, there must be some salty liquid that can conduct current that induces this magnetic field. And so this is very circumstantial evidence for the presence of liquid water in this particular moon of Jupiter's called Europa. But a few years later, the Cassini spacecraft, which went out to the Saturn system, transmitted back this phenomenal image of another moon, Enceladus, where you see these gigantic geysers or plumes of water that are shooting out of cracks of this moon into space, some about 400 kilometers, right? And so this is proof that there is liquid water out there in the solar system. And they conclude there must be jets venting from subsurface reservoirs of liquid water. And so suddenly we realized that out in the outer solar system, there may be copious amounts of water. And so here's a sort of an overview slide that shows our estimates of the amounts of water on different moons in the Saturnian and system and around Jupiter. And what you see is that when you the blue ball, everything is to scale here, right? So the moons are to scale of Earth, and the blue balls are to scale the estimated volumes of water in these bodies. And the truly surprising thing is that some of these moons may actually have more water than the Earth, right? And so this really changes the game in terms of habitability, right? Now the question is, what generates? Why is there water out there? Everything is cold. And the thought is that all these moons orbit the giant planets, Jupiter and Saturn, and they have very strong gravitational forces that deform these moons and cause a lot of tidal heating. And on the right-hand side, there's different kinds of tidal heating, and you can see that Europa, Titan, Ganymede, they get quite a lot of tidal heating. So there is if you're too close to Jupiter, then you get too much tidal heating and everything melts and all the volatiles leave, and you have sort of an Io type body that has essentially actual volcanism, rock melting. If you're too far out, then you don't get enough tidal heating. But in particular, Europa is in sort of a sweet spot where you get a lot of tidal heating that essentially melts the ice in the interior, but it's not so much that you essentially strip off the volatiles over time. And so, this was discovered approximately 20 years ago, and has now led to 3 big missions that are coming up to explore these icy moons, in particular ones that are thought to have large volumes of subsurface water with dedicated missions. So the Europeans are supposed to launch next year the Jupiter Icy Moons Explorer, and that will visit multiple moons in the Jupiter system. Then the one that everybody here in Austin is excited about is Europa Clipper, because we have people that work on the radar of this mission, and that will study Europa in particular by and hopefully give very detailed information about the ice shelf thickness and so on and so forth. And then there's the, much later is going to be the Dragonfly mission that's going to go out to Titan, and the idea is to fly this octocopter around Saturn and study Saturn. Now, this for the first time sort of, allows us to test the hypothesis that fundamentally water plus, energy gradients plus nutrients plus a lot of time should make life, right? And so it would probably be one of the major things, if we would find any evidence for life on these bodies. And so typically, right, the search for habitability is follow the water, right? So now we found the water, and so we can say, so what, right? And so now the question is, well, would this water be habitable? And, there are many, many steps, nutrients, energy sources. So we'll just take the next step, and you could, obviously different people would choose different steps. But so one simple question is, would there be energy that the chemotropic life could exploit to, sustain itself? And so, the most obvious source of energy here is life exploiting oxidation reduction reactions, which give you an electron flow that plants can make use of, and for that matter, animals can make use of. And so on Earth, the source of the redox gradient in the ocean is clear, right? You have an oxidized atmosphere and seafloor weathering, whether at these black smokers or just general serpentinization of the seafloor produces hydrogen. And so that's one source of a redox gradient. An interesting question then becomes, well, what if this is an internal ocean, right? So we don't have an atmosphere that's rich in oxidants, but as it turns out, this is an image of Europa. You see all this brown crud. Europa's ice is continuously being bombarded by ions and just all sorts of particles. And they're actually oxidants. The ice is being broken down into oxidants by this bombardment. And this is something that the astronomers can see spectroscopically. So there's a source of oxidants on the top of the ice. And presumably at the bottom of this internal ocean, there is some sort of rocky seafloor that, certainly in chemistry, isn't that far from our own seafloor. We don't know if it's basaltic or more peridotite or chondrite composition, but it's going to have, certainly serpentinization reactions are likely to occur there. Whether they have black smokers or not is a different question. But one of the questions that's sort of indicated here in the schematic diagram is, well, how would the oxidants that form at the surface make their way down through the ice into this ocean, right? And then there's all sorts of papers, are we oxidant limited? Are we reductant limited? So on and so forth. And you can clearly see here that the author here is sort of indicating a plume, some sort of descending plume of heavy cold ice that may be dragging the oxidants down, right? So that's like a proposed, in terms of a drawing, an oxidant transport mechanism. So that's the key. How would the oxidants get down? And so back in the day, when around 2017, that nobody had actually sort of tried to make any kind of mechanistic model. So that's something I got interested in and that we've been working on. But the first thing is to essentially come up with a near surface oxygen inventory. And here really this was my pandemic hobby. We're following the previous work by Kevin Hand, 2006 and 2007, but we're working with some, Purva Oza helped us to kind of try and understand how people estimate these things. But basically you have the idea that you've got ions, electrons, photons coming here into the ice. The ice is thought to have a porous regolith on the top that's generated by continuous impacts of tiny meteorites on the Earth. We don't have this because the atmosphere would just burn up these tiny meteorites. But on bodies like the moon that don't have an atmosphere, you get this continuous these continuous impacts. And on the moon, it generates this kind of dust. And so people assume that something similar is happening also on Europa. And so the idea would be that the very top few grains in this regolith would be bombarded, and the H2O in the ice structure gets destroyed, the hydrogen escapes, and what's left behind, and what the astronomers can see spectroscopically, are these odd O2O2 molecules, and they have a particular, vibrational mode that you can see. And so when I say oxidants from now on, I just mean the O2 essentially, but there could be other oxidants, and so in that sense we have a lower bound, if you like. Now, so from these spectral observations, you can guesstimate that somewhere between 0.3 and 12%, in a number basis is the abundance of this O2 to H2O in the photon penetration depth, which is really shallow. But now the thought is that this impact gardening churns this regolith, this porous regolith, and that at least within the porous regolith, essentially, we have a similar oxidant abundance, okay? Because it's being turned over, and every time it gets to the surface, it gets bombarded, but then it gets stored at depth. Now, estimating the depth of this impact gardening regolith is fraught with uncertainty, so you could have anything from a few tens of centimeters to meters. Porosity is also not known. And if we put all of this together, we can estimate that the amount of the oxygen just in moles on all of Europa's surface is somewhere on 10 to the 14 to 10 to the 18 moles, right? Sounds a lot, of course, on a global scale. This is not a lot, but it's better than nothing. Now, if there's any kind of deposition, like, on Enceladus, we see these geysers, right? And eventually the stuff falls back down as snow. Then you would continuously bury these oxidants, and you could essentially saturate a much deeper layer with oxidants. Now, this is some people here at Greenberg have speculated that this process is so efficient that you would essentially oxygenate the entire ice shell. That's, of course, an extreme assumption, but it is entirely possible that some of this deposition could saturate hundreds of meters, maybe the top kilometer, with these oxidants. And that, of course, would give us a bigger reservoir. So when we started, essentially the only estimate for the rate of oxygen delivery to this internal ocean, here in kilograms per year, was to say, okay, we have this total amount of oxygen, and we think Europa's ice shell is like no more than somewhere between 10 and 100 million years old. This is largely because it lacks many impact craters. So we can just divide the total amount by this time scale, and that gives us a rate. And so this would be, the oxidant delivery rate by sort of wholesale crustal overturn. And when we compare this to photosynthesis on the Earth, you see that, we're talking 5 orders of magnitude less oxygen delivery to the ocean than is produced by photosynthesis, right? So clearly we can't hope for whales and penguins and whatnot, but maybe some microbes, some slime down there. So we got in there when saying, well, can we make some mechanistic model of this oxidant transfer, right? And really, there are 3 mechanisms. So here are the mechanisms that have been proposed. So the first one is the idea that you just keep depositing stuff on the material on the top, and you keep melting but the ice shell has a constant thickness because the heat flow is given by the interior. And so if you put stuff on top, it needs to melt at the bottom. And so this becomes just a conveyor belt that transports the oxygen through the ice. Once we have actual real observations of actual cryovolcanism or plumes on Europa, I think this becomes a mechanism that's interesting to model, to think about. Other things that have been proposed is impacts, right? If you have an impact that penetrates the ice layer, like the one shown here by Rona Cox and one of her collaborators, obviously you're bringing ocean water to the surface, and you could get it in contact with the oxidants on the surface. Several people early on actually already realized that we may have melts that are quite shallow, and there's some evidence that these melts actually make it to the surface, it's thermodynamically hard because the surface is very cold, but there is that suggestion out there. And then if those brines, so the thing is that brines, of course, are dense relative to the ice, and so if they are formed and if there's permeability, then you would expect some drainage of these melts. And then the other one is the one that we saw in this other picture, is some form of convective, solid state convective overturn. And so what we chose to do is we chose to look at these three processes. And as I said, so all of these were class projects. In 2018, we began looking at impacts on icy moons. And this was eventually then turned into, like a derivative of that was eventually turned into a model of oxidant transport, or in general mass transport from these impact melts. Then we looked in 2019, we actually built a model for brine drainage through ice. And then 2 years ago, we looked at convective overturn. Okay, and so everything I'm presenting here is essentially sort of research projects from the numerical modeling class, which has been fun. So starting, backwards. So let's start with ice shell convection. There are two papers led by Evan and by Natalie, came out last year. So what is the observational evidence for subduction? I mean, it's of interest all by itself, oxidant transport or not, to have another body that would have something like plate tectonics. And so people have searched quite intensively to find some evidence. And there is, I think, reasonably good evidence presented by Simon Kattenhorn and Proctor, that there is a relatively small region where you can argue that something has been shoved on top of something else, right? And they're very careful to not call it subduction, but subsumption, because, I guess subduction actually means that it would make it down into the convecting ice shell. So there's some evidence for that, but really it's very, if you step back and you get over the excitement to have found this, it's actually very limited. It's a tiny area where you could argue that has been subducted overall. So while there's some evidence, it's clearly not something that jumps out at you on Europa. So now on the modeling side, there's been much more work as usual, right? There's a whole generation of ice shell models. So here's early work by Toby et al. And this is actually, despite the graphics, which are French noir, as I like to call it, but it's actually one of the better models. It's kind of sophisticated, and includes melting, includes all sorts of things. And one thing that you see here is that it has a very thick, what we call the conductive lid, and that is because the ice is highly viscous, is highly temperature dependent, and so up here the ice, of course, is very stiff. And this leads to a thick conductive lid. So there's a strong asymmetry in the conductive boundary layers. So here's some other work. This looks much prettier, but you can see that there's no asymmetry. So they probably are isoviscous. There's a surprising number of isoviscous models. Here's another isoviscous model, but they look at the evolving thickness of the ice shells.
That means that they want somebody by October 26th, right? Or like.
Sorry. Should I continue, or is there was this a question?
I think somebody accidentally unmuted. So okay. Go ahead and keep going.
Okay. Anyway, so people have looked, interesting. So the amount of heat coming out of the interior may change, and so the ice shell may thicken and thin. Here's some more sophisticated model that Sam Howell and Bob Papalardo put together. It has all the lithospheric deformation, the fracturing. What you can see again here is it's a very thick conductive lid. And of course, people have done 3D modeling using, whatever large-scale code. And so the question partially was, what could a class project possibly add to this? And so one thing that turned out interesting is, for whatever reason, all these pre-existing models assume that the thermal conductivity of the ice is constant. But Natalie Wolfenbarger's pandemic hobby was to look up all sorts of thermophysical properties of ice. And what you can see here is that ice thermal conductivity actually increases quite rapidly as the temperature declines, right? So Europa's surface temperature is somewhere between 100 and at the poles a little bit lower. So you see that the conductivity doubles or maybe even triples. And you say, well, that's not an order of magnitude change difference. But then the change in thermal conductivity, right, of course, thickens the conductive lid, but it's the feedback with the strongly temperature-dependent ice viscosity that makes this a big deal. So you just need to drop the temperature a little bit to increase the ice viscosity a lot. And so that's why this turns out to be actually quite significant. So Natalie came up with her favorite parameterization of all the published data. And so the question is, what is the effect of this on convection, right? So we make standard convection model, so Stokes equation, Arrhenius type viscosity. So we assume it's Newtonian, so there's no, and so there's a Rayleigh number here that is essentially a ratio of advective to conductive heat transport. And then we need an energy conservation equation, and at the top here it's written in terms of temperature. But we were interested in a model where all the properties are temperature dependent. And so then it becomes useful to just write this in terms of the enthalpy once the heat capacity is temperature dependent. And so you can rewrite the energy equation as an enthalpy conservation equation, which is written here. G is a tidal heating term that depends on the viscosity. And so there's a dimensionless number that is essentially the ratio of tidal heating versus the ratio of conductive heat loss. And there's another parameter, which is essentially the homologous temperature. So it's of the surface. So it's the surface temperature relative to the melting temperature of ice. So we have three dimensionless parameters. But so right now here we're looking at a case, and I have some backup slides with tidal heating, but we've just turned off tidal heating. We have, the surface is about 1/3 of the actual melting temperature, and the Rayleigh number is somewhere 6 × 10⁶. And so what you see is something very similar to these simulations by Toby, where you see a very thick conductive lid. And then in the lower, let's say 2/3 of the ice shell, you see these convective rolls. And that is assuming a constant thermal conductivity, right? So so if you use the lower bound, so I forgot to say this, there were two previously published relationships. One was sort of the lower bound, which is what people in planetary science use. You see that the conductive lid has thickened quite a bit. If you use our best fit, it's very, it's again, the conductive lid has thickened a little bit, but if you actually use the upper bound on the thermal conductivity, then you see that the entire ice shell is stable. And just because I didn't point this out before, let me just show you, right? So these were the two previous relations that had been published by Rabin. So the brown line, so that's what I refer to as the upper bound, and the Hobbs one is the lower bound, and the one that we eventually used or prefer is somewhere in between. But so what you can see here is that because of this feedback between temperature dependence of thermal conductivity and then the temperature dependent viscosity, you can actually stabilize the ice shell just depending on, you can go from a very happily convecting ice shell to one that is stable, but just by choosing different thermal conductivity relationships. Now, here we've made a little regime diagram. On the bottom is the Rayleigh number. On the vertical axis here is the homologous temperature of the surface. And then these different lines give essentially the boundaries between the conductive and the convective region. And you can see that as you go to more conductive, to these temperature dependent thermal conductivities, that boundary moves by at least an order of magnitude and maybe even almost 2 orders of magnitude. And of course, we've judiciously chosen the example here so that you can transition from unstable to stable by switching between these different things. But the overall thing is, no matter which one of those relationships you believe, that the strong temperature dependence of the conductivity and of the viscosity generally in the system tend to lead to very thick conductive lids. And of course, we don't have the brittle deformation and the kind of things that you would need to truly induce subduction or something like that. But it is very hard. It's going to be very hard to get anything down through this thick conductive lid with, in some convective way, right? And so steady state type convection like this is unlikely to transport any oxidants. Now, of course, if you had a massive thermal perturbation, right, that would change things. So convection, at least steady state convection, is probably not going to help us. But one of the things, so the previous simulations that I showed didn't include tidal heating, just for simplicity. But if you include tidal heating, it turns out that tidal heating is the highest at temperatures close, at viscosities close to the melting point of ice. And so in that lower conductive part of the ice shell, you're going to start dumping a lot of tidal heating, which raises the temperature even more. The temperature of that part is already close to the melting point. But here I've shaded in red the regions that if you include tidal heating, where you actually raise the temperature above the melting point of ice. And so all of these regions should be partially molten, right? Or are in this case partially molten. And the reason the convection cells look different is because we've taken the change of density due to the partial melting into account here. But this essentially tells you that even in the absence of salts, which could lower the melting point, this lower half of the ice shell is very susceptible to partial melting. Yeah, and so it's likely widespread. And so this motivates then the question, well, you know, could this lead to any brine drainage, and could that brine drainage lead to any oxidant transport? So there was an early paper by Jake Jordan that was it was not on Europa, but it's sort of on mass transport and porosity waves. And that sort of set the stage. And then we had a later paper on applying this to the oxidant transport in Europa's ice shell. Okay, we're not the first ones here to think about brine drainage. Gaidas and Nimmo suggested this sort of in a hand-wavy way in 2000. Sotin similarly, but it's really Klara Kolosova at the Karls University in Prague who developed the first sort of real model. So what you see here is from her 2014 paper, where she assumed that heating along a strike-slip fault generates melt in the near surface, and that's the black line. So we have porosity as a function of depth. And then she allows it to evolve, and you see these little bumps here, and these are porosity waves that kind of just happen naturally in these types of systems. And you see the brine draining down. But this didn't really consider the transport of oxidants. So we thought, well, let's see what happens if we add oxidants to that. The only abstract that mentions oxidant transport by brine drainage is an LPC abstract, though that didn't have any quantitative. So, you know, if you go back here, right? So yes, there are brines, right? But the brines are clearly in the lower half of the ice shell, right? So that's not going to help us get stuff down from the surface. So, but one of the fascinating things about Europa is there's something called chaotic terrains. And here's a map showing that these chaotic terrains cover approximately a quarter of Europa's surface. It's everything that's shown in green. And these chaotic terrains, nobody really understands how they form. But when you look at these, so the top here is essentially an image from Galileo, and below is essentially a made up little sketch of how people think it forms. But when you look at this, it looks like the ice shell has somehow been broken up, and there's big sort of icebergs or ice shelves that are floating around. So the dimensions of this could be hundreds of kilometers across. And in between these ice shelves that are floating that seem to be intact, there's kind of mushy stuff, poorly defined mushy material. And as I said, it's very difficult to imagine how this actually forms because the surface is so cold, and how do you get it? It takes a lot of energy to form this. But you know, whatever explanations for this are out there, they all imply that partial melting happens in that very top of the ice shell, right? And people have pointed out, of course, that energetically this is very difficult. So this definitely requires a perturbation. And we're going to kind of assume the bottom left plot here, right? Conceptual model. So there's some warm upwelling in the ice. That means this warm upwelling likely is also, there's partial melting here in this warm upwelling. And then the thought is that the increased melting near to the surface is due to the fact that near the surface you have more salts that lower the melting point and that allow sort of copious melting near the surface. So it's essentially a eutectic melting point reduction. And we're not arguing for any of these models. We're just saying, well, what if that would happen? What is the consequence of that? So is there any evidence that these brines that something brine-like has come to the surface? And there's, again, spectroscopic evidence of irradiate sodium chloride that seems to be associated with these chaotic terrains. And that is something that people point to as evidence for somehow melts getting to the surface where they could get in contact with oxidants. So the challenge here is shown by the figure on the right here, right, where you see the steady geotherm and with a really, really thick conductive lid and then a convecting region below. And really, if you want any of this to happen, you have to bring that geotherm, the convective geotherm, essentially to the surface, right? The brown area is sort of the salt-enriched area, where if you did this, then you could suddenly induce more melting, but it clearly requires a quite substantial perturbation. Now, there are salts, right? And different salts have different eutectic points, but salts only help so much because if you want a lot of eutectic melting, you need to have a lot of salt. and we can discuss. I have backup slides if that's of interest. So what we're going to assume here is, chaos formation typically is implied near surface melting. We're going to assume that we have near surface melting, and we're not going to try and model the mixing of the oxidants into the brine. We're just going to assume that we have a near surface melt with brine in it. And then we're just going to ask 3 simple dynamic questions, right? For this brine to sink down and transport these oxidants, the ice shell must be permeable. This turns out was a big debate at the time. And then the brine must drain faster than the refreezing. So, and then finally, the brine must transport oxidants, which wasn't actually obvious at the time. So there was a lot of debate here, but I will argue that if you have partial melting of a wetting fluid on a polycrystalline material, you will form these grain boundary networks that tend to connect at very low melt fraction. Again, I have backup slides if we want to discuss this. Now we're going to make a really simple model for brine transport. We're going to have mass conservation for the brine and the ice. Rho is the density, v is the phase velocity. And we're going to really just add 2 simple constitutive laws. One is Darcy's law for the relative fluid flux of the brine velocity relative to the ice velocity. And then we're going to add a simple compaction relationship that says, if there's a difference in pressure between the brine and the solid, then there is a divergence in the solid velocity, and there's a coefficient here, a compaction viscosity that's hard to define, but to first order people assume it's related to the shear viscosity of the solid. And if you substitute those 2 relationships in, you can come up with 2 relatively straightforward evolution equations. So this is for purely mechanical system. We actually couple this to a eutectic phase behavior. So there's sort of an energy and a composition equation that get added to this. But I'm not going to discuss this. And this system has an internal length scale, which is called the compaction length, which is the distance at which you can communicate changes in pressure through this sort of partially molten slush. And because we don't know how these chaos terrains form, we're going to assume a very simple model. So my preference is, if you don't know, then make it simple. We're going to assume a relatively low melt fraction ice shell with and near the surface, we're going to have an increased melt fraction. Okay. And then we're going to assume that the trace has been mixed into this near surface layer of increased melting. And then we can run a simple 1D simulation here. And you can see that, and so the point, and to actually, because there's not a lot of salt up here in this layer, you actually need to essentially raise the temperature almost to the melting point of ice to get this. So we start off with just a uniform temperature. And you see almost error function-like conductive boundary layer. Here you see that in the second column, you see the porosity evolution. What happens here, where the porosity is larger initially, the melt flow is much faster. And so the brine essentially runs down and accumulates in some sort of a pocket above the lower permeability porosity ice shell. But there it exerts an overpressure and eventually dilates the underlying ice, and then you see a porosity wave forming, very similar to Kalosov's work, that migrates down in approximately 20,000 years. The third column is just the salt volume fraction. So very near the surface, there's some eutectic freezing, and then you see the oxidant is actually being transported here down through the ice. Now, earlier work had shown that the amount of tracer you transport depends highly on the dimensionality of these porosity waves. So here we have a little cylindrical example, which allows us to compute actual volumes of melt transported, and with that actual amounts of oxidants. So here's just a number of different times. Red is the oxidant, blue is no oxidant. The white colors, the white lines are essentially porosity contours. And you see some very similar behavior. You see the porosity wave forms. These are these circular contours here at about 10K. And then a cute detail is that within this porosity wave, you have this kind of swirling transport of the oxidants down. But in the end, actually, we get the same result in approximately 20,000 years. Here we drain this brine. The main result here is that the brine can escape the refreezing from the surface and drains faster. And so, we can use this. We can use our knowledge of how much oxidant there's on the surface, what fraction of the surface is affected by this chaos formation, what fraction of the oxidants is delivered through this porosity wave, and the mean surface H, and we can estimate or guesstimate an ocean delivery rate, which is somewhere around 10 to the 6 to 10 to the 10 moles per year. So it's obviously lower than the total crustal overturn, but it can bring certainly a majority of the oxidants down. And let me see what, okay, so the biggest criticism of this work has been the initial condition, right? But the initial condition is something we just don't know. So we thought next we'll work on something where we have a much better guess what the initial condition is. So the question is, can these impacts transport oxidant? And so there was an early paper that we wrote in the first class, and that just looked at the lifetime, how long it takes to freeze one of these impact chambers. And we have a more recent paper that looks at the evolution, the dynamic evolution of these impacts. So the basic idea was that, of course, if you have a really big impact that penetrates the entire ice shell, then the water comes up and potentially gets in contact with oxidants. But on Europa, there's no evidence for penetrating impact craters, although certainly there have been some in the past, but it's clearly not something that happens regularly. Actually, this paper by Cox and Bauer suggested that maybe chaotic terrains are formed by penetrating impacts, but apparently that's not a very popular suggestion, although I think it's as good as any other explanation. But similar, people are also very much interested, not on Europa, but on Titan, on giant impacts, because Titan has a surface that has oxidants and it has a deep ocean that has water. And if you had a penetrating impact, it would bring the water and the organics together and would sort of would form what the authors call the perfect cradle of life, be that as it may. Now, again, now in Titan, there is evidence for craters that seem to have penetrated the ice shell, but unfortunately, the Dragonfly spacecraft will not land to this big impact crater, but to a much smaller impact crater that likely didn't penetrate the ice shell. So we asked ourselves, well, what about smaller impacts, right? So there clearly are more small impacts than there are big impacts. Could an impact that doesn't penetrate the ice shell still lead to vertical mass transfer? So here's something called the Mannanen impact. All these impacts are named after Celtic deities, and this is the only one that's pronounceable. So that's why we've chosen it. It's shown here. And so people assume regularly that essentially you form obviously melt, right? And so here, for example, people speculate that this melt then could be sourcing sort of plumes of vapor that get deposited, right? But the question is does that really make sense? Is that really the fate of these impact-generated brines? Because when you look at these impact simulations, and so these are Rona Cox, who ran the original impact simulations, she shared her results with us. So this is, the end 12,000 seconds or something of one of these impact simulations. So here she assumed a 10-kilometer ice shell, so a little bit thinner than what we typically work with. And what's shown here is the porosity, or if you like, the melt fraction, right? And so these impact simulations, if you take them at face value, predict a rather large, fully molten cryomagma chamber, if you like, that goes several kilometers down into the ice shell, right? But that's not the only thing they do. So if you look at the thermal structure of after the impact, right, typically have a very cold conductive lid that, of course, is extremely rigid. But the impact, of course, also dumps a giant amount of energy into the surrounding ice. And what you see is that they essentially warm up the ice. And in fact, I mean, my student here has been lazy. So the actual ice-ocean interface kind of domes up to maybe 2 by 2 kilometers. And he was lazy and just filled it in with ice at the melting temperature. But all this ice beneath this impact chamber is very soft because it adds melting point. So we have brine, a giant volume of brine that is dense, above very soft ice, right? And so my question was always, wouldn't this just sink or founder down? And so if you put this in a simulator, just a standard Stokes simulator in cylindrical geometry, this is, of course, exactly what happens. So the top shows you the temperature. The red line is the boundary of, temperature 0 Celsius. And on the bottom, it shows you the melt fraction. And what you see here is that, of course, this heavy brine cannot be suspended above this soft ice, and so it sinks down. The thing that is truly surprising here is how quickly this goes, right? Now note, in the previous work, we've actually assumed porous flow. Here we don't assume porous flow. This would probably help the process, but here we assume that simply the dense brine sits in little bubbles that are disconnected, so they can't flow, and they just weigh the ice down, okay? Clearly, eventually you'd want to integrate these different processes, but here we looked at them separately. Now, here about 80% of the melt, or I think it was 34 cubic kilometers of melt that are formed by the impact, and about 28 or something like that drain into the ocean within 1,000 years. So now, of course, if you make the impact smaller, so here's an impact that has 17 cubic kilometers, and here one has 7 cubic kilometers, and you see that the 17 cubic kilometer melt chamber sinks and eventually makes it to the ocean, but it takes longer, and this is mostly because the thermal field is less perturbed and the ice is still a little bit stiffer. And of course, then if you make the impact chamber even smaller, there comes a point where, yes, it begins to sink, but it refreezes and it doesn't drain, right? So clearly there are non-penetrating impacts that allow vertical mass transfer. And so the reason we chose the Cox and Bauer data set was they did a huge number of simulations because they were trying to determine the ice shell thickness from impact structures. So they did 10, 20, 30, 40 kilometers. And because they assumed essentially a linear conductive temperature gradient, really you can think of this as the thickness of the conductive lid, if anything, because once you would get into the soft convex ductile ice, you would surely continue sinking. And so, we ran all of their non-penetrating impact simulations and found that, you can take the transient cavity depth as a fraction of the total ice thickness. And if that transient cavity depth of the impact exceeds about half of the ice shell thickness, then you begin to drain melt. Okay, and this is for all different ice shell thicknesses. So there seems to be a threshold somewhere around 0.5 ratio of the cavity depth versus ice shell depth. And then again, we can take the catalog of different impacts on Europa. We can combine that with our guesstimate of how much oxidants are on the surface. We can make assumptions about the conductive lid. And so for a 10-kilometer conductive lid, craters that are wider than 16 kilometers would lead to melt drainage. Here we assume that 50% of the oxidants within the crater are delivered. We recently found a paper that actually tried to guesstimate something similar, and they came up with 20, but it'd be the same order of magnitude. And so we come up with the amount of ocean delivery, which would be somewhere around 10 to the 1 to 10 to the 5 kilograms per year. So that is significantly less than we get from chaos drainage. But the main difference here is not the inefficiency of the process, but it's just that a relatively small part of Europa's crust is affected by impacts today. In the past, this may have been different when there have been more impacts. So with this, I would just like to wrap it up. So, we've been interested in the habitability of these icy ocean worlds because it seems that there's more liquid water in the outer solar system than in the inner solar system. And this has sort of really expanded our idea of where life could be. And we argue that, if you want life in these internal oceans, you need to somehow supply a redox gradient. And the key step there is trying to get oxidants that form by energetic bombardment on the surface of the ice down through the ice. And so we were trying to come up with different physical models of how this would work. We looked at convection, but there's a very thick conductive lid that needs to be overcome. Now, a huge thermal perturbation like the one that we imply to generate chaos terrains might change this picture as well, but sort of standard convection, I don't think we'll get any oxidants down. We've argued that if you somehow manage to generate large amounts of partial melting near the surface, and there is observational evidence for that, then these brines could drain before they refreeze and could deliver a significant amount of oxidants to the ocean. And finally, we looked at these impacts, and we argued that even impacts that do not penetrate the ice, the melts generated by these impacts would if the impact is big enough, would founder through the ice, and they may certainly transport all sorts of things vertically through the ice, including potentially oxidants, although there's all sorts of questions, what happens to these oxidants on the surface if they're affected by an impact. And with this, thank you for your attention. I'm happy for any questions.
Great. Thank you, Mark, for the fascinating talk. So it's our department's tradition for students to ask questions first. So John, is there anyone in person who wants to ask a question?
This is called student hazing.
I've asked the room and nobody has raised their hands, so we can go with anybody online.
Anyone online can unmute yourself and ask a question.
I guess, yeah, that's very far from what you guys are doing, right?
I think then we can open up question to anyone in the room or online.
I had a question about application of the downward transport on a snowball Earth, getting communication between the atmosphere and the ocean.
Yeah, I mean, I actually haven't really thought about snowball Earth, but it's probably one. Yeah, I mean, so snowball Earth, right? The ice shell would partially sit on land and partially cover the ocean, but in the ocean portion, I have no idea how thick people think the ice shell of a snowball Earth is. Presumably not 30 kilometers, right? But certainly, if you had any localized melting events, whether that's due to some impact or some volcanic activity, or just some seasonal, like a warm summer on a snowball Earth. I mean, my main argument, right? So the oxidant transport is sort of, is icing on the cake, but there's a significant fraction of the community and many nature papers that claim that there are large volumes of melt very shallow in the ice, right? And this is tempting because you could try and sample that. I personally think that that you would drain any of these melts, whether it's by porous flow or fracture flow or diking or just viscous overturn. I don't think in the long term you could sustain large volumes of dense brines in the shallow ice, just because to have brine, the ice needs to be relatively warm and without relatively soft. And so, one of the things that the Europa Clipper mission, the radar, is going to look for is shallow melt pools. And I guess I've just put myself out there saying I don't think those exist. Unless they were lucky and were like in the process of forming one of those by some thermal perturbation. But I don't think you can sustain them over long times.
Okay, I think we have another question.
Mark, I had a question. Thanks for your talk. I was wondering, most chemolithotrophs on modern day Earth live at redox gradients that are relatively stable and relatively steep. And I wonder if these mechanisms of the impacts or the brine percolation could make redox gradients that are both stable and steep.
So yes, so you're rapidly exceeding my knowledge of microbiology and things like this. So I doubt, right? Any of these, like all of these, I think are episodic events, right? Maybe early on in the history, right, there was significant bombardment, and you could sort of argue that continuously you have sort of impacts that are draining down, but clearly today, I think these are episodic events. And so in that sense, I think they would not be stable, right? Whether they would be steep enough would depend, I guess, on the fluid, sort of the dynamics of how this is exactly delivered. But yeah, I mean, it's, I mean, I think these are open questions, right? And it'd be kind of disappointing, but it's entirely possible that we have these giant volumes of water out there that are totally sterile. But yeah, it's just interesting to, but yeah. So the thing is, right, on Mars, we've been looking for water every time we find like 3 molecules or some trace, like it's a Nature paper. But so here we have something where I think we're fairly certain that there is volumes of water. Now we can ask all these other questions, right? What would it take? I mean, there's also interesting questions about nutrients and so on and so forth. But yeah, so I mean, I'm trying to think who are the, people like Kevin Hand are actually probably better versed with the actual habitability. I'm sort of the fluid mechanics guy, and I'm just like trying to think of how the oxidants get down. But I think it's a totally legitimate question. Whether, I guess in my modeler's mindset, I would like an equation. I would like some system of ODEs where, like, you deliver oxidants and reductants and nutrients and maybe some substrate, and then it tells me how many microbes there live there. But I'm not sure if these kind of models are any good. But it seems that you would have to, yeah. I mean, how many bugs would this feed, right? And if so, for how long? Clearly is the next question.
Thank you.
Any other question? I have one, Mark. There are many questions that came to me, but one thing is I was really inspired by that you did this through series of courses. And I'm just hoping to hear a little bit more about how you did that. Like in your geologic science program, was it junior level class, first of all? Was it junior level?
Well, we have a geophysics program, and in the geophysics program, yeah, juniors or seniors, depending how they schedule their stuff, take this numerical modeling class. And when I took it over, it was like integrating with the Euler method forward, backward. So I found a lot of numerical methods classes rather boring, because you try to, like, I don't know, differentiate things 4 different times, 4 different ways. And so I thought I want something that's oriented towards some purpose, right? And that also shows how you can do something. The actual need how this came about was that I went from 10 grad students to 0, and I took over this new class, but I also had this research project that I was doing. And I was like, well, I'm either going to develop this new class or I'm going to do this research project all by myself. And so I decided to make this research project the class project. This was back in 2000, and it worked out reasonably well. And students it could have been a total catastrophe, but students seemed to like it. And then sort of, I just came up every year. There was a new question to kind of think about. What makes it possible is that we essentially, fundamentally what we do is we just build a discrete divergence gradient and curl, and then you just need an advection operator. So you build like 4 different matrices: a divergence matrix, a gradient matrix, a curl matrix, and an advection matrix. And then with tensor products, you can go from 1D to 2D or 3D if you want, relatively without much effort. And then you just need the time derivative, which is trivial. We just do the theta method. And with this, so by building these sort of Lego building blocks, you can just say, okay, now we solve Stokes. Now we solve, heat conduction. Now we solve this 2-phase flow problem, which is a Helmholtz equation. Or when we did Mars. So it turns out that, and actually I started using it's a surprisingly simple approach that works surprisingly well. And the students seem to like it. It's very different from writing lots of for loops. There's no for loops. It's all just it's surprisingly compact and surprisingly fast. So it's fun.
Very, very cool. I really hope to talk more about it in the later opportunity.
Yeah, anytime.
Yeah, it's actually 5 now. So is there any last question, or otherwise we will, I guess, end here. Okay, thank you again, Mark.
Thanks so much. Thanks for inviting me. And yeah, feel free to contact me anytime if you have any questions.
I will. Are you coming to AGU, Mark?
I'm still debating it.
Okay.
It's tempting, yet there's so much to do.
I hope you do. And if so, I will see you there.
Okay, yes.